Hello everyone, I am Dr. Ritish Kumar. In this lecture, we will discuss about the Klystron amplifier. So in this lecture, we will cover the topic related to Klystron, such as construction of the Klystron, working principle of the Klystron, working mechanism, and the limitations of the device at higher frequency, why we will use the Klystron at higher frequency. So we will discuss in this lecture. So let's begin. So first we need to understand the limitations of the device at higher frequency. The frequency beyond 1 gigahertz or roughly we can say 1000 megahertz, the inductive and capacitive effects comes into the picture. The limitations of the main limitations in the conventional tubes are interelectrode capacitance and lead inductances. Second one, electron transit time, gain, bandwidth, product. So we will cover these three limitations in details. So interelectrode capacitance, in other terms we can say stray capacitance, Bayer capacitance, or these are the other names of interelectrode capacitance. And lead inductance, we can say Bayer inductance as well. So suppose at higher frequency, these effects comes into the picture. Suppose if I consider a device triode, so this one is cathode, this one is grid, and this one is anode. And this one is grid. So these are the electrodes. At higher frequency, the capacitance is generated in between anode to a grid to cathode, and anode to cathode. We can give the name as CGA, CAC, and CGC. So due to generating of this interelectrode capacitance, the performance of the device definitely would disturb, and we can say the efficiency of the device would decrease. The reactance of the capacitance we already know that Xc is equal to 1 upon j omega c. If we increase the frequency, definitely the reactance of the capacitor would decrease. That will affect or decrease the performance of the device. So the another term is lead inductance effect. So how this effect, how this inductance would disturb the performance of the device. Again, I am drawing the triode valve here. So this is cathode, this is grid, and this one is anode. So lead at higher frequency, all leads have some inductance effect. It acts as an inductor. Suppose if we want to apply input signal from this point B in, and due to the presence of this inductance, Bayer inductance at higher frequency, so as we know that the reactance of inductance is j omega L. As the frequency increases, the reactance of inductance would increase. So definitely if we apply some input voltage here, this inductance will drop the voltage from V into some quantity that we can say V naught. So the actual voltage that is applied at the triode valve is V in minus V naught, which affects the performance of the device here, and we can say due to this reason the efficiency of the system or gain of the system can decrease. So this one is another effect that we can consider here at higher frequency. The next one is the electron transit time. So electron transit time, what is the electron transit time? Electron transit time is the time taken by the electron to reach at the anode from cathode. So this is cathode, this is grid, this is anode. So time taken by the electron from cathode to anode is called transit time, right? So here we can uh, by activating the cathode, electrons are generated and it passes through the grid and reach to the anode, as we know the general phenomena of it. By applying some signal at the grid, we can disturb the path, we can control the path, or we can control the movement of the electron from cathode to anode. Suppose if we apply the low frequency signal here, and another one is the higher frequency signal. So before at low frequency signal, the electron movement is fast comparable to the phase change of the signal. So the path of the signal would not disturb. The path of the electron would not disturb from cathode to anode. If we apply the higher frequency signal, it can be possible to have the polarity change in the polarity change before reaching the electron from cathode to anode. So if the polarity changes from plus to minus, it can possible to have the oscillation of the electron in between grid and the cathode, and due to which the some of the electrons could not reach at the anode. That's why the performance of the system or performance of the device or we would decrease, or we can say the efficiency of the device would decrease. This is the another effect of the higher frequency, another effect of the device at higher frequency. The last one is the gain bandwidth product. As we know, the gain bandwidth product is the constant we can write. So if you for the higher gain, to achieve the higher gain, we need to compromise with the bandwidth here. So if you increase, so we can say bandwidth is the some constant divided by gain. If you increase the gain, then definitely the bandwidth would decrease. So but at higher frequencies or for higher power, we need to have wider bandwidth. For the application of satellite, we need to have a device which has a wider bandwidth and higher gain. So these two conditions we can have by using such kind of microwave tube such as TWT, that is known as traveling wave tube as here. So to overcome these limitations, we have some kind of cavities that is known as retrained cavities. Retrained cavities can be used in the Klystron amplifier. So to overcome these limitations, we use Klystron amplifier, reflex Klystron, magnetron, and TWT. TWT is used to have wider bandwidth and higher gain simultaneously. This is all about the limitations of the conventional microwave tubes at higher frequencies. So next one, we will discuss the two cavity klystron and the construction of the two cavity klystron here. So this is the architecture or constructions or we can say the inner architecture of the klystron. So here, why we call the two cavity klystron amplifier here? So first we need to understand two cavity, then amplifier. Why we call the amplifier? So definitely amplifier is nothing but it amplifies the input signal and we receive the higher amplitude at the output side. That is the basic terminology of the amplifier. So in the case of two cavity klystron, you can clearly observe here this one is the cavity. This is known as buncher cavity and this one is known as catcher cavity. Both cavities are looking in a similar structure. We can say both has the symmetry with each other. So we can say the buncher cavity also known as input cavity and this one is known as output cavity as well. Why we call? Because this cavity is drawn near to the input signal input of the device and the catcher cavity is made at the output side of the device. That's why we call input cavity and output cavity as well. So this is a cathode. This is a cathode. This one is anode. RF input signal here, drift space we can say, and these all the things we will learn in detail one by one. So this is the cathode. Now superficially we can I can tell you the basic principle of the device is the velocity modulation. How the velocity modulation can happen in this device. So cathode, when we this is the DC voltage V0 that is applied to the cathode, and cathode always generate the electrons. So electron stream is generated through the cathode and these this anode provide the focusing effect over the electron so that the electron can direct it towards the collector or we can say it can be directed towards the buncher cavity, catcher cavity and collector by with the help of anode. This provide the focusing effect. Now suppose this cavity here you can see we have applied the RF input signal here. Suppose there is nothing input we have applied initially. So whatever the velocity of the electron has, it does not affect due to the presence of this cavity, because you haven't applied the RF input signal here. Now you can see here V0 is the velocity of the electrons and Vt1 is the velocity of the electron after passing through the buncher cavity, we can say after leaving through the cavity. And we here you can clearly see here the gap of the cavity is represented by d, 0 to d. So this gap is d and this cavity gap is again d. Whatever the process whatever the changes we can have only in the region of this cavity gap. This is the main cavity gap where the electron movement, the control of the electron movement can happen by applying the RF input signal here. So superficially if you apply the RF input signal at the input cavity or buncher cavity, so definitely when the electron enters at this point at the input cavity, the velocity of the electron would change due to the presence of this RF input signal, and this effects we can have at the output of after leaving the cavity here, this velocity is changed. This velocity is changed. Now due to the presence of this RF input signal, the velocity is changed Vt1 from V0. So we can say the velocity modulation can happen due to the presence of this buncher cavity. Now velocity modulation means the change in the velocity, of electrons. So this is called as velocity modulation. Now how the amplification can happen in this device, then we can discuss in detail in the next coming slide. So now this modulated electrons beam passes through this catcher cavity, then, and the electrons now in this region is this region is known as drift space, and in drift space the bunching of the electrons happen, or we can say this is bunching area as well. Bunching of electrons happens, and these bunched electrons passes through the catcher cavity, and these bunched electrons release their energy in the form of current, and these current we can have from this RF output signal, and this signal is amplified signal with respect to the input signal. So, and all the electrons or electron beams is collected by the collector here. So this is about the basic working mechanism of or architecture of the two cavity klystron here. So here some important points you need to see here. T0 and T1, T2 and T3 are the timing scale, and if we say what is the transit time of this buncher cavity, we can say T1 minus total time travel by the electron from entering to leaving point, that is called T1 minus T0, that is the transit time for buncher cavity, and the transit time for catcher cavity is T3 minus T2, and the space of gap of on both the device is D. So this is the construction of two cavity klystron amplifier. Now the velocity modulation, how the velocity modulation takes place in the klystron device, so klystron amplifier. So this is the RF signal that we have applied at this buncher cavity. So here you can see the positive half cycle, negative half cycle, positive, negative half cycle. This is inputs RF signal. So so in the case of positive half cycle, it can be possible to increase the velocity of the electrons at this point, we can say, and this is zero crossing point, we can say, and this is negative half cycle, maximum amplitude or negative half cycle. So at the zero crossing point, the electron velocity does not affect, and at the higher at this region, the positive half cycle, the velocity of the electron can increase, and the lower negative half cycle, the velocity of the electron would decrease, and due to which and this cycle is repeated due to the presence of the RF signal, and bunching can happen at this in the drift space, as we discussed in the last slide. This one, in this region the bunching can happen. Bunching happened in this space due to the presence of this RF signal. Now the thing is, the transit time, due to the transit time of the electron movement in the buncher cavity is represented by tau is equal to T1 minus T0, as we have discussed in the last slide, and the space between the gap between the cavity is d, and the speed, the velocity of the electron is v naught before entering the cavity. That's why the transit time is equal to dy v naught here. Now this, as we know that the kinetic energy is equal to static energy, so half mv naught square is equal to E into V. So from where EV naught, because we have applied the DC voltage is V naught. So here V naught is equal to, from this equation we have twice EV naught by M, and this is comes from this equation. Now the thing is how the amplification is happened. This is the basic principle. The basic, if somebody asks what is the basic principle of the Klystron amplifier, always we can say the basic principle of the Klystron amplifier is the velocity modulation or current modulation, we can say. So this is about the simple mechanism of the velocity modulation. Now, as we have in the construction point of view, the velocity is changed after leaving the cavity. So, why? Whatever the change is always happen due to the presence of this buncher cavity. So initially we find initially we find the kinetic energy equal to static energy, like half m v naught square is equal to E into V naught. Now, because suppose RF signal is represented by Vs here, suppose if you apply the RF signal here, then this equation would change from half m v naught square is equal to E V naught plus average of Vs. So this is the average of RF input signal. So we need to find out the average of the RF input signal that we had applied at the buncher cavity here. Now you can see the equation here. This is the average of RF input signal. Why we applied the this limit T0 to T1, because buncher cavity has the timing, the electron movement timing from T0 to T1. That's why we have applied the limit T0 to T1 V1 sin omega t. Here this is the average of RF input signal after opening this limit. We have this equation, and after applying this cos C minus cos D formula, we have this equation after applying cos C minus cos D formula, right? So here you can see this factor is represented by beta I, which this is known as the beam coupling coefficient of the input cavity gap. So this is nothing but a sinc function, we can say, sin theta z by 2 upon theta z by 2, where theta z is the transit angle, omega tau. Tau we already know, T1 minus T naught here. This is already discussed in the last slide. So this is nothing but a sinc function. So we by looking this graph, we can say by increasing the transit angle, the magnitude of the beam coupling coefficient would decrease. So this is the main parameter of the velocity modulation process. Beta I is the beam coupling coefficient of the input cavity gap. Now the velocity modulation process continues. Now, how it comes? We already know that half, as we discussed, half mb square Vt1, we can say E V naught plus Vs. After putting the value of Vs from the last slide, we have Vt1 like this. So this is a modulated, we can say modulated velocity of the electron. This is modulated velocity of the electron. So if I compare this equation from the amplitude modulation, this one is 1 plus mt sin omega ct. So this one is known as depth of velocity modulation, or we can say modulation index. Velocity modulation index we can also say like that. Depth of velocity modulation is equal to the velocity modulation index. So here beta e v1 divided by v naught is the depth of modulation. Now, by applying the binomial expression, we have the alternative form of this equation, because we can consider this is the whole power of 1 by 2. So v naught this is simple v naught. If Bs, average of Bs is equal to 0, so half mv naught square is equal to ev naught. So v naught is equal to square root of twice ev naught by m. So this one is v naught, we can write here, this one is v naught. Now the power of half, if I consider power of half, 1 plus nx. So beta e v1 divided v naught half. This half comes into the picture by applying the binomial expression. So if this now here you can observe, here this is plus sign, this is negative sign. Why? Because if you consider t naught, then you need to consider plus sign. If you consider t1 means the leaving time, then you need to consider a negative sign, because you are treating, or you are dealing the change in the velocity within the cavity. So that's why this sign is changed from with respect to t naught and t1 here. So this is the velocity modulation equation. So this is the depth of, in the both cases, this one is the depth of velocity modulation. Now, bunching process. Amplification is happened in the Klystron amplifier due to the bunching happened in between the drift space, or we can say the space between the buncher cavity and the catcher cavity. Here, this space, drift space. So in drift space, this bunching phenomena is happen. As you can see, this is a zero crossing point, this is positive maximum amplitude, this is negative maximum amplitude. So at the zero crossing point, the velocity of the electron does not affect, while for the positive half cycle, the velocity of the electron will become faster, while in the case of negative half cycle, the velocity of the electron would become slower comparative to the reference electron, that is the zero crossing electron, due to which at some point in between the drift space, the bunching is happened. Due to this bunching, most of the energy, or maximum of the energy is maximum energy contained within this bunched condition. So this bunched electron when pass through the catcher cavity, if this bunch of the electron beam pass through the catcher cavity, or this catcher cavity in this catcher cavity, these bunched electron release the energy of they release their energy in the form of current, and this amplified output we can take out from this catcher cavity. So this is the process of having the amplification of the two cavity klystron here. So this bunching phenomena is occurring repeatedly by applying the RF input signal. So this is all about the Klystron amplifier, that we need to understand how what is the construction of the two cavity Klystron, what are the limitations of higher frequencies, and working mechanism of the two cavity Klystron, and how it amplifies the RF input signal by changing the velocity of the electron. This is the all about the two cavity Klystron amplifier that we had discussed till now. So thank you.